All right, young scholars. Today we're going to be covering sorting. And this week will be our last programming assignment, although the next 2 Thursdays after that, we'll still do some in-class examples of programming examples during our Thursday meetings. There just won't be any homework associated with it. So hopefully you like that this Thursday will be the last homework assignment, and then it's just the final exam and that group project, either your hangman or your tic-tac-toe game. So why would you want to think of sorting or study sorting within computer science? Well, think of it in real terms. Who has like a collection of anything? Like sports cards, stamps? Nobody? Well, let's say you have a collection of... Grace, you have a collection?
When I was younger, I had a sticker collection. I
Okay.
once in a while grabbed some, but not all the time.
So you probably organized or sorted them in some way, right? Like,
Yeah,
oh,
got a book.
you might have had like on one page of the book was all, unicorns. On another page was all cats. The same idea applies within computer science with sorting. You have different algorithms available to you to sort for, let's say, strings, integers, doubles. And as you've seen basically throughout the semester, a lot of these different ideas can be enhanced using loops, for, if, else, while, even cases. So as I mentioned, you could sort data based on what specifically it is. So most of the time, data is going to be stored as an integer. Remember we did last week with the priority queuing? When we had them as integers, we had to set the array as an integer type. When we had it as strings, we had to set the array as a string type. So as long as you have your data set up or stored correctly, you're able to sort it. If you just, said string X equals George, string Y equals Tyson, sorting that not really going to be helpful. The idea is to grab information from an array and sort it that way. That's why it's so important to understand the element and the index. How the element starts at 1, the index starts at 0 in Java programming. So your first element is an index 0, your second element is an index 1, etc. So the first type of sort that exists is called an insertion sort. Should be fairly simple and straightforward to understand how that works. Every time you insert a new variable, in this instance, we have all integers, it keeps getting moved until it is where it needs to be. So in this example, 2954,816. By the time all of those numbers are sorted, the 1 is pulled in front of the 2, the 4 is pulled in front of the 9, the 5 is pulled in front of the 9, the 6 is pulled in front of the 9, the 8 is pulled in front of the 9. So you end up 1, 2, 4, 5, 6, 8, 9. Then if you were to insert a new integer, let's say 7, where would it go? Where would 7 go? If we inserted 7 here, 1, 2, 4, 5, 6, 8, 9, where would 7 go? We're missing a 3. We're missing a 7. So where would the 7 go? In between 2 and 4? In between 4 and 5? Where's the 7 going to go? In between the 6 and 8, right? So the 7 would be inserted after the 9 initially, and then up, it's after the 6, not after the 9, and be moved, just like you see in the other examples. Oh, the 1 should be first. We got to move the 1 all the way over there and move everything back. It's much easier when you only have 2 numbers that it needs to be put before. What if I were to add 17 to the list? Instead of 7, we now have 17 inserted. What would that do?
It would just stay at the end of the numbers.
Yep. It would just remain there because it's after 9. What if we had 3.5? Where would that go?
Isn't that a double, so it would have an error? Or would
Nope.
it go
It would
between the,
truncate. It would get rid of the 0.5 and just make it 3 and drop it in between the 2 and the 4. So
okay,
because it's an integer, it just gets rid of the decimal place. Now we could always set up, as I showed you with exception handling, please enter integers. And then they would have to enter 3.0 instead. What if I put 4? What if I inserted a 4?
it would go between the, oh, would it just go after the other 4?
It could. It could be placed after the other 4 or before the other 4. We'll never really know because it'll just say 1, 2, 4, 4, 5. So we're not sure which 4 will come first or which 4 will come second. What if I put 1? Same idea. It'll either go after the 1 or before the 1. We'll never be sure because it'll just say 1, 1. So here's another visual of how that would work. What do you think the gray boxes mean? We have 1 gray box, 2 gray box, 3 gray box, 4 gray box, 5 gray box, 6
The
gray
gray
box,
boxes mean
7
they're
gray
sorted.
box. Yep. The gray boxes, okay, we've looked at all these numbers and now we're moving the sort. Okay, we've checked 2. Now we're checking 9. Okay, we've checked 2 and 9. Now we're checking 5. Okay, 5 is less than 9. We got to switch them. Now we're checking 4. Okay, 4 is less than both of them. We move it. Now we're checking 8. Okay, 8 is less than 9. We switch them. Now we're checking 1. Okay, 1 is the smallest. So we drag that up to the front. Now we're checking 6. And then we move 6 ahead of 8 and 9. So in essence, when you're doing an insertion sort, you're checking each number one at a time. That's why just like here, you see there's 7 steps. Same thing with these images. First step, second step, third step, fourth step, fifth step, sixth step, seventh step. Now, once you have it initially sorted, and then you just add to the my list of the integer, then it becomes much easier. Oh, okay, 7 should go right here. It's before 8 and after 6. Oh, 3 should go right here. It's after 2 and before 4. So here is kind of that in textual language. It sorts a list of values by repeatedly inserting an unsorted element in a sorted sublist until the whole list is sorted, which is basically all of these steps. Just keep moving the numbers around until they're in order. So, you learned probably in grade school your numbers 1, 2, 3, 4, 5, 6, 7, 8, etc. When you insert them through an array and do an insertion sort, Java's a computer, on a computer, it's used to zeros and ones. So it has to interpret the numbers you're putting in. Oh, okay, this needs to go here and this needs to go there. But what do you notice with the elements here? What do you notice? What are the elements matching here? Always when it comes to an array, an element goes with a what?
The index.
Yep. So if 2 is our first element, the index is 0. If 5 is the second element, the index is 1, etc. And for example, here, we're using those indexes. If 4 goes before 5, we have to move what's currently in our index 1 over to 2 to drop our 4 in. See here? Move index 1 to index 2. So now the 5 is in 2, and the 4 gets dropped into index 1. So if you were to technically print out to a print line after each of these steps, as Java is compiling and going through it, you might have 6 or 7 different print lines. And you'll see more of this on Thursday when we do some of these sorts in class. So why are we using a for loop here? Why do you think we would use a for loop for a insertion sort?
So that because it has like a condition, you want to insert until like each number is in the list and then it's sorted.
Yep. You keep going. If you have 27 numbers, you don't want to stop after 5, right? You want it to keep going. You get whatever your list dot length is, the size of that array, how many integers are in it, how many elements, and you keep sorting. Okay, you do the first index. Okay, you do the first and second index, first, second, and third index, and so on and so forth, until all of the numbers are properly sorted in order. 1, 2, 3, 4, etc. But you might want to add a new integer. So in this instance, we're running our for loop until all of our integers are sorted. But we could set it up where we're going to keep adding a new integer. So we insert a new element into the list. It could be, let's say we have our numbers 7, 4, 3, and 2. Once the sort first happens and goes through all the steps, it's now 2, 3, 4, 7. What if we add in the numbers 1 and 12? What happens? What happens? Where does 1 go?
I think before the 2.
Yep. It would start off after the 7 and then ultimately be placed before the 2. Then the 12, it would start off
After
Yes.
7.
and stay there. No change. So with an insertion sort, it initially will start off at the end. So see here, 7, 4, 3, 2. 2 is technically last in the array we created, but it needs to go first. Okay? But it doesn't know that until it goes through all the steps. Okay, 4 is before 7, it switches them. Okay, 3 is before 4 and 7. Okay, it switches them. Oh, 2 is before all of them. Then it switches them. Then when you add 1 to the end, oh, we know it's before all of them. We plop it in the front now. When we add 12, oh, that's the biggest. Okay, that'll stay on the end. And that's insertion sort. Basically, keeps changing everything until everything's in order. Then there's bubble sort. What do you think you see as the difference here with bubble sort? Do you see it, the pattern here?
They grow in rows.
They go in rows, okay? What,
Diagonal.
what other pattern do you see? Do you see the yellow highlights? What do you
Yeah,
think
it's
those yellow highlights represent?
it goes until it reaches a higher number.
Yep, so with bubble sort, the numbers are simply swapped. So the new element is swapped with the old element on the right if it's smaller than the left. So 2 and 9, which one's smaller?
2,
2 stays on the left. 9 and 5, which one's smaller?
5,
5 moves over to the left. Make sense? Which one's smaller? 4 or 9?
4,
4 moves to the left. Which one's smaller? 8 or 9?
8,
8 moves to the left. Which one's smaller? 1 or 9?
1.
1 moves to the left. So in this first instance, we have 2, 5, 4, 8, 1, 9. That's not really in order, right?
Yeah, it's still out of order, so it'll go again.
So it goes a second turn. Is 2 or 5 smaller?
2,
2 is smaller, stays on the left. Is 4 or 5 smaller?
4,
4 is smaller and moves to the left. 5 or 8, which one's smaller?
5,
5 is smaller, it moves to the left. 1 and 8, which one's smaller?
1,
1 moves over to the left, 8 moves to the right. But we're still not in order, so we have to go again. So 2 stays left, 4 stays left. Is 5 greater than 1?
Yes.
So it moves over to the right, 1 moves to the left. So now we have 2, 4, 1, 5, 8, 9. We're still not in order though. We got to go again. So the 2 is smaller than the 4, that stays. But the 1 is smaller than the 4. So now the 1 moves left, the 4 moves right. But we're still not in order. We got to go again. Oh, the 1 is smaller than the 2. So the 1 moves left, the 2 moves right, and now we finally have our order. So think of it like when you're blowing bubbles, right? Are they all the same size? None of you have ever blown bubbles before?
No, they're all different sizes.
Right. That is essentially the bubble sort. Okay, we got some over here that are a little similar, some over here that are a little similar. We kind of have to use our eyes to put them together. Whereas the insert sort is basically, oh, okay, 2 goes before 1, 3 goes before, or excuse me, 1 goes before 2, 2 goes before 3, etc. Bubble sort, instead of those different just changes, goes through what are called passes. It'll compare everything on the list, then go again, compare one less row, compare again, one less row, compare again, one less row, compare again until it's done. So why are there 5 passes here? Can you guess from looking at the screen?
To ensure that nothing needs to be switched.
Okay, true. But how do we know that it's going to be 5 passes before it's solved? What gives that away?
There are 5 initial rows in the first pass.
Not necessarily. What gives it away?
5 numbers. 6
5
numbers.
numbers? 6 numbers, yes. We have 6 numbers. Elements, indexes. Index is always one less. Same idea applies with the bubbles. If we had 8 numbers, we would definitely need 7 passes to get them all in order. And we'll go through an example of that on Thursday. So what do you think a merge sort is?
Something that sorts out the numbers in order.
In order? That would be a sort. Have you used Excel before? What is to merge in Excel?
It's to combine 2 different cells.
Okay. So in a merge sort, it's more or less the opposite. We have 8 numbers in a cell, if you will. We split them into 4 pieces each, split them again into 2 pieces each, split them again into 8 pieces, and then basically put it back together. We split 2, 9, 5, 4 from the first half. Yeah, 2 goes before 9. That's good. Up, 5 is less than, or 5 is greater than 4. We got to switch those. Okay, now it's 2, 9, and 4, 5. What do we do? The 4,
We
5.
put the 9 at the end of the 5.
Yep. The 4 and 5 get dropped in between the 2 and the 9. So we have 2, 4, 5, 9 from that 2, 9, 5, 4 we had in the first piece. But then the second piece is 8, 1, 6, 7. We break it up into 8 and 1 and 6 and 7. And the same idea. The 1 switches with the 8 first, but the 6 and 7 are both smaller than the 8, so they get dropped in the middle. And then when we merge them all together, oh, okay, the 1 goes before the 2, that works, drop it. The 4 and 5, the 2, 4, and 5 go before the 6, 7, and 8, okay, drop that in. The 6, 7, and 8 go before the 9, okay, drop that in. And then lastly, the 9. So which seems more simpler from what you've seen so far? Insertion, bubble, or merge sort?
I think the insertion.
The insertion. Now, the primary way or reason you would use a merge sort, what do you think? What do you think the big reason to use it would be? When would you think of using a merge sort?
Perhaps if like you have like a large group of numbers.
Yep. You tend to want to use a merge sort. Let's say you have 84 numbers you want to look through. Much easier to do it with a merge sort because it's breaking the pieces up and putting them back together like a puzzle. Whereas the insertion sort is going to literally go through number by number by number by number, which is going to take quite a bit of time. So here's how you would technically set that up. And again, we'll see this more on Thursday. You would have your first half numbers, your second half numbers, and then merge them together to form your full completed merge sort. So here is a more similar example compared to how it would look compared to an insertion sort. We're taking 1 from the second list because that is the smallest number, right? Then what do we take next?
Take the 2 from the first list.
Yep, you drop the 2 in, then what's next?
And then the 4 and the
Yep.
5.
Then the 4 and 5 from the first list. Then what?
And then the 6, 7, 8 from the second.
Yep, 6, 7, and 8 from the second.
And
And
lastly,
then
the 9.
last, the 9 from the first list. So the 2 goes next. Then the 4. Then the 5. Then the 6. Then the 7. Then the 8. Then the 9. However, what do you notice with this list compared to, let's say, a bubble list or insert list or insert sort? The 2 lists have to be the same amount of what?
The same amount of numbers.
Yep. So you have 4 in your first list, 4 in your second list. You can't have like 9 total. It can't split half a number. You'd have to have an equal number in each piece in order to merge them. So if you had 5 in your first list, you'd have to have 5 in your second list. So the idea is, as I mentioned, you would use these, as Zaza said, the more numbers you have, the more likely you would be to use the merge sort because it's going to take less and less amount of time. So here's the big, I don't know, what would that be? Pre-calculus formula behind it. With the total time is broken down by a logarithm. In essence, as both Zaza and I said, the more numbers you have, the less time it's going to take with the merge sort compared to a bubble sort or an insertion sort. But then there's probably everybody's favorite, which is called the quick sort. You all had that, what is it called at Bloomfield? Spreadsheet Essentials class?
No, well, not me.
No?
I had it. Sometimes you have to take something else. Computer literacy.
Uh,
It's either computer literacy or spreadsheet essentials. It's one or the other.
okay. Well, those of you that had the Spreadsheet Essentials, did you learn about pivot tables?
Yep.
So Amelia, explain to us what a pivot table does.
I don't remember. It
You
was a
don't
year
remember?
ago. And
That
I
was a
don't use
year ago.
Excel.
You don't use Excel? So
It
basically,
was not important to me.
it's not important to you?
No, surprisingly, it's not doesn't come up that often in my daily life. Yes.
Okay. So basically, the idea behind a pivot table is you're going to have a table of data. And you're going to try and basically pull out some of that data based on what you need. Let's say you have a table Maybe it would help if I just pull open Excel and create a pivot table. Let's say names, heights, salary. Okay, George, Bob, Linda, Carol, Tommy. He's just gonna be 5 feet tall. He's gonna be 5'9". She's gonna be 7 feet. Carol will be let's say 4 foot. And Tommy will be, let's say 7'2". Tommy and Linda are a big family. So salary, let's just say they're all 50K, just for the heck of it. So if I wanted to create a pivot table, I would select all of the data from the table. Destination. Okay, fine, just make a new worksheet. So they all had the same salaries, right? So what purpose would including the salary matter? It won't, right? So we would use names and heights, and then we could use modifications. Let's say we just want the people that are taller than 69 inches. We'd have to change our nope, not count of heights. I guess sum of heights works. Then we would use our, let's say, top 10 filter and say top 10% of the sum of heights. And it should cut down to whatever the top 10 is. But the point is, with a pivot table, you have certain pieces of information that you want to pull out and only use those pieces of information. Like I said, with the salary, it's all the same. We don't necessarily care then. They all have the same salary. Quicksort is basically the same thing. Like if we put in all of our names in a Java program and said, oh, okay, here's my favorite sports team. Here's what I like to do for fun. And then you asked for that specific information. That's all you'd be granted. So if we created an array of the numbers 52938401167, what do we notice? What are we noticing? We're breaking it into 2 sections. 42130. What are we doing with that section? We're cutting out the 42130. What do we do with it?
That section is then sorted.
Yep. 0, 2, 1, 3, 4. Up, we move 4 to the back. Up, do we really need the 0? Up, now we changed it to 1, 3, 2, or 1, 2, 3 rather. So it would end up as 0, 1, 2, 3, 4. So if we only wanted those 5 pieces, you could in theory throw out the 0. Because when you write a number, are you going to write 0, 1, 2, 3, 4? Or just 1, 2, 3, 4?
Just the 1, 2, 3, 4.
Yep. So that's exactly what the quicksort is. So the array knows that the 0 is still there, but, we don't write out, 0, 1, 2, 3, 4 as a number. We just write it 1, 2, 3, 4. If it was a decimal, we'd probably put 0.1234. But as a whole number, we wouldn't have that specifically there. So do you think the quick sort time is going to be quick?
It should be.
Yes. But again, it's like the insertion and bubble sort. It's quicker when there's less numbers. The more numbers you add to the quick sort, the more time it takes. It's not as much time as the others, but it's still going to take more time. So let's say it took 30 seconds to do that sort for, what was that, 5 numbers? If you went and did 87 numbers, it might take 2, 3 minutes. Whereas an insertion sort might take 4 minutes. Now, those are just, giving you a time reference. It's probably not actually what's going to happen. Because as you've seen, computers are quite skilled and go through what they need to do in quick amounts of time. But there are what are called worst case times. The worst case time is the absolute worst possible situation. Like when you have, let's say in class, for example, what's the worst case scenario when you're taking a class?
Failure.
Yeah, failing it and having to repeat it, right? But then the best case scenario is what?
Again.
The best case scenario, what would that be? Passing? How is that best case, Franny? You just want to pass and be done?
Or learn.
Learn, okay, that's good. You
Getting
want
an
to get an
A.
A, right? You want to get that A. So in this example, when it comes to your quick sort, your best case time is the quickest possible time, which rarely happens. The worst case time is the longest possible. But what happens more often than not is the average case time, the average of your worst and best case. So let's say the worst case, it takes 7 minutes to go through 87 integers. So worst case, 87 minutes. Or no, what did I say? 7 minutes for 87 integers. Say best case is 3 minutes for those 87. What's the average of 7 and 3? What's the average of 7 and 3? Add them together and divide by 2.
Five.
Yes, 7 plus 3 is 10, divided by 2 is 5. The reason is you might have larger numbers on one side of the pivot as opposed to the other. So let's say you had, a all single digit numbers on the one side, that goes very quickly. You had all double digit numbers on the other side, that takes a little more time. So it'll average them out. So we're going to talk about trees in 2 weeks. So we'll hear more about heaps then. But a heap is a data structure for designing efficient sorting algorithms and, as you saw last week, priority queues. It's a complete binary tree, and each node is greater than or equal to any of its children. And like I said, when we go through trees, I think it's 2 weeks from today, you'll have more of a clear understanding. But a complete binary tree is which one?
Would it be the first one?
The first one, yes. What else?
A third?
The third? Are you sure? Is she right? Who agrees with Grace?
The first and second.
The first and second? So you disagree with Grace about the third one?
Sure.
Sure. Are you just going by what the slide says?
The slide does have the answer in it. I'm just using all my resources.
So explain why 3 is not complete.
A and B are complete, binaries are not complete. Binary tree is complete if every level of the tree is full, except that the last level may not be full and the leaves of the last level are placed leftmost. They're not placed leftmost.
They're not placed leftmost. See? In order for this to be complete, Grace, that 14 would have to be where the 22 is, and the 22 would be right here. And the 33 would be where the 14 is.
Okay.
So this would be here. That would be there. And then it would be complete.
Okay.
Make sense? Why is this not a heap in the second one? I'll give you a hint. It's underlined.
The root 39 is less than its right child, 42.
Right. So for this to be a heap, it would have to be like the first example. 42 is greater than 32 and 39. But 42 is greater than 39. So this is not a heap because we don't have a parent bigger than the child. And like I said, when we touch on trees more in depth in 2 weeks, this will be quite clear, but I'm sure you're already happy that there's no programming assignment associated with it. So here is how you would represent a heap. All of your childs or children have to drop down to smaller sections. 62 goes down to 42 and 59, both smaller, good so far. 42 drops down to 32 and 39, good so far there. 59 drops down to 44 and 13, good so far there. 32 drops down to 22 and 29, good there. 39 drops down to 14 and 33, good there. 44 drops down to 30 and 17, good there. 13 drops down to 9, good there. But what if I added 58 there? What did I just do?
You made the child greater than the parent.
Yep. So 13 is no longer a heap. It's dead to us. So when you're adding elements to a heap, it goes through this pattern to basically check what the biggest number is. So in the list of 3, 5, 1, 19, 11, and 22, what's the biggest number?
22.
22. So notice in our completed, our parent is 22. What's the next highest number?
19.
19. Goes off to the right. What's the second highest?
11.
Goes off to the left. What's the lowest?
1.
So that will be dropped off with our 19, which is our highest child. And then the 3 and the 5 will be dropped off with the lowest child. If we had 2, where would it go?
It would go underneath the 19, like next to the 1.
Yep. What if we added 8? What would happen?
It go underneath the 11, next to 5 and 3.
Nope. We'd move the 3 over to the 19. The 5 would go where the 3 is, and the 8 would go where the 5 is. So the lowest children will go here. The highest children will go here. And these are each called nodes on the heap. So if you were to add 88 to that, it's going to initially start off where there's empty space. Then, oh, okay, it's greater than 19. It's going to trade spaces with the 19. Oh, wait, no. It's greater than the 22 too. Now it bounces all the way up to the top. So it switches with the 19, then it switches with the 22. So if I put 8 in here, is it going to switch with the 19? Nope, not big enough. But what if I deleted from a heap? Let's say I deleted the number 62 here. What would happen? What takes over now?
The highest number, which would be 59.
Eventually. But first, we have an empty child here. The 9 would initially move to the top. So this way it's not just floating out there. Then, oh, the 59 and the 9, the 59 is bigger. It would switch back up. But then what's going to happen with the 9 and the 13? The 9 now switches with the 44 and is on the same level as the 13. You see that? 44 is greater than 9. It switches. So now the 9 and the 13 are on the same level. And then the 30 and the 9, which one's bigger?
30.
So the 30 becomes the parent there, and the 9 drops down to the child. So this is all done through the heap class. So heap parameters creates a default empty heap. Then you could add objects to it. What kind of objects do you think you could add to a heap? What kind of objects? Strings, circles, chickens, eyeballs? What kind of objects? Primarily, it's going to be integers and doubles that you're going to be able to add objects to a heap. As you saw, it just makes it easier to move and sort everything around. So we just saw and looked through a couple slides that, hey, which one's bigger? And then we just changed or sorted the heap around. However, again, just like all the others, our programming compiler has its own thinking of how long these should take to complete, which is called the heap sort time. And again, we have this long-winded pre-calculus calculation that computes it. But in theory, that is tied with trees. And like I said, we'll cover that in 2 weeks. Whereas this week is just to focus on our good old sorting. So in class on Thursday, I'm going to go through a couple examples like the bubble sort. And so the task due next Monday night for the last homework assignment is going to be to use sorting that will sort numerical numbers in an array from smallest to largest. What are your options? You could use a bubble sort, there's insertion sort, merge sort, whichever example you're most comfortable with based on what we go through on Thursday during the examples. So if there are no questions, I will bid you all adieu and see everybody on Thursday. Like I said, even though this is the last programming assignment, we'll still do on Thursdays programming the next 2 weeks after this Thursday. So what is that? The 9th and the 16th. We'll still show you example programs in the Thursday class meeting. All right, so if there are no questions, I'll see everybody on Thursday.
All right, thanks. I'll see you Thursday, Professor. Bye-bye.
Bye.